Craig Young.
All right. So good morning, everyone. Thank you for joining me on this early, crisp Toronto morning. Any 5K runners? Congratulations. For me, I think I do a 5K every day before noon, just trying to walk to lunch in this center here. So I'm Craig Young, Chief Technology Officer for Swift, and I am delighted to be kicking off day 3 of InnoTribe. The linking theme on today's presentation is about innovative technology and business. And for me as CTO, this is something near and dear to my heart, and not for the obvious reasons around revenue generation and cost reduction, but rather on creating an engaging workforce. When you understand the value of the work you're doing, it creates a much more rich team, and in fact, makes it much easier to attract and retain talent. With us here today, we have an authority on artificial intelligence and high-performance computing and how that's changing the financial services industry. Give me a warm welcome for Dr. Go. So, Dr. Go joined Silicon Graphics back in 1989, and in 1998 he became their chief engineer, and in 2000 was named their chief technology officer. And after their acquisition with Hewlett-Packard Enterprise, he was named their vice president and SGI chief technology officer. He has been named one of the most influential CTOs in the industry and is on many of the ones to watch lists that come out annually. So with my pleasure, Dr. Go, I'll turn it over to you.
Thank you very much, Craig.
Thank you.
Thank you. Thank you for coming so early in the morning. I have only 2 goals today. One, that you enjoy yourself, and 2, that you at least learn one thing new that could be useful for your business. So you can see that AI, high-performance computing, and financial services industry, that's the reason we are here today. And the way we're going to do it is with understanding that AI, there are 2 approaches. The top-down, traditional, and the newer bottom-up approaches, right? And that I'm going to focus on the bottom-up for predicting the future. That's what we are here, right? Same with science and engineering, same with finance. Let's have a look at what top-down is, the traditional approach. That is, you ask your analyst, your quant, to build your models first. Then based on that model, you input your current condition and hope you can predict the future. Right? In many of these examples, predict whether there is a cyber attack, predict what the stock price will be, predict what the option pricing should be. But first, you start with building the models. And the models are based on 2 things. If possible, if there are laws that everybody agree that is always true, you use it. If there are no laws, you build your own rules. Just like life, right? If there is laws, you rely on them. If not, you build your own rules at home, right? Yeah. There we go. Let's look at science first. Let's look at an example of a law. That's an 18-wheeler truck right at the bottom there. And this is the size of a tornado forming. There is a law that tells you if you run your thermodynamics equations, you can determine roughly where the touchdown point is of that tornado and where the path of the tornado would be. We're not quite there yet. We're getting it right 1 out of every 3 times, right? But we're getting there. And all these are based on a set of laws called thermodynamics equations here. Now, the first 2, there are 3 laws there. There are 3 equations there. The first 2 predated the Nobel Prize, but the third one won a Nobel Prize. Yeah, that's why they're called laws. Okay, right. Cyber in the top down. I'll give you an example of rules if there are no laws. What's the law that says that a cyber attack is coming? Well, there is none, right? So you rely on rules. This is an example from one of our customers in Japan, NICT, N-I-C-T, that's detecting all the IP packets coming from a remote location to their location and identifying in yellow what those IP addresses are. They set a rule. There are many, many rules in there. Say, for example, if an IP address was dormant before, and it starts to send me the first 2 packets, I'm gonna suspect that that's gonna be the start of a DNS attack from that location. Has been commandeered. So there is no law there, no equation to help you there. So someone sat down and wrote an equation, an if statement. If IP address was dormant before and sent me 2 packets, do something, right? That's a rule. So laws and rules. No laws, write rules. Yeah. And that's how we lived all these years. That's what your analysts, your data scientists, and your quants have been living all these years. So you are a senior manager, you tell a quant, build me a model. He or she goes back and does one of these. In stock pricing, yes, you have written rules. You may not know it, but they have written rules. For example, that's a 50-day moving average of that stock price, and the other one is a longer-term 200-day moving average. And you can write a rule, right, to say if the 50-day exceeds the 200-day, buy. That's a simple rule, but you can make it more complex, right? I will only buy, if this is true, I will only buy if it is not a Friday and if it is not raining, right? You could start to expand on those rules, and that's where your differentiation comes in, because you consider more and more things. Yeah? Option pricing. You can write rules, right? If my stock price or exercise price goes up, right, the call option should go up, and the put option should go up a different way. You can write those rules, but the problem with those rules is that there are so many things to consider. They cannot get it all right, and that how much should the stock price go up relative to the exercise price, and who is more important? Now, you don't have that in a rule. However, there is a Black-Scholes law. Now, it's a derivative of a law, yeah? And a lot of your quants do this, right? It does not determine your option price, but it gives you guidance, because it considers the delta, right, the D, the cursive D that you see there, are the rate of change, yeah, of the different parameters below. And it takes all these into consideration, how fast each of the different ones are moving, and tells you what the call price should be and the put price should be. So if you can find a law, right? And guess what? Why do I call the Black-Scholes-Merton equation a law? Well, it was awarded a Nobel Prize. Yes, a Nobel Prize in economical science. Turns out that Scholes and Merton were awarded a prize, but the equation is called Black-Scholes. I think there's a bit of fairness there, because Black passed away before the prize was awarded, and Nobel Prizes are not awarded to, you're only awarded to people living, right? So we call it Black-Scholes instead of Scholes-Merton, right? Yeah. But Merton got the prize. Yeah. Yes, there we go. Anyway. Any more laws that you use? Well, if you're building a negotiation system, right? A system that negotiates, a system that auctions, there is incomplete information there, and there is a new law that people use, and that's called the Nash Equilibrium. Your quants may have started using that. Who watched the movie A Beautiful Mind? Yeah, that's him. John Nash discovered it. He was awarded the Nobel Prize. You see? Laws are called laws because the Nobel Committee decides so, right? Okay. Again, remember, if there are no laws, you write rules. But the problem with rules is that you cannot keep up. And the problem with laws is that crazy behavior breaks them. Just like Black-Scholes, right? You cannot handle black swans, for example. So therefore, we look at bottoms-up approaches. This is the new and emerging, re-emerging, I call it re-emerging method. And people call this machine learning, but I call it bottoms-up, without the S. Right? All right. Yeah. Maybe tonight with the S. Right. And what do? No model. I'm not going to go to school and study physics. I don't care about rules. I care about nothing. I just care about your past records. I shouldn't say you shouldn't go to school, right? Still need to study physics, yeah, and do your STEM courses. But this kind of approach says that I don't want to know about the model for a good reason. Because models can be wrong, models can be incomplete, right? Let's use your past records that has observable behavior and say that I'm going to predict the future based on your past within a certain limit. Yeah? So what do you do in this new world of bottom-up? In the Black-Scholes model, instead of writing the equation out, because you don't care about it, you take what matters in the equation, and each of these 4 or 5 or 6, you can add more, you can add weather in, right? You can add the time, day of the week in there because it affects behavior. You can put all that in there, and each of these is one record. But the thing is, you need lots of records, right? In the recent deep learning approaches, they are talking 1 million records. Right? If they say if you have less than 50,000 records, maybe it's not enough. What do? They basically feed each record in there, and then they say, predict for me after the first record. And if it gets it wrong, never mind. I have another 900,999 tries. That's basically what it is, right? I shouldn't say this in an AI conference, that basically AI is guessing, right? But basically, that's what it is. Just remember, you're just sending enough tries so that you eventually guessed it right. If you get it wrong, never mind. They will tweak the relative importance of each of the inputs. They'll keep tweaking it. And after 1 million tries, eventually you get the tweaks pretty good. And ultimately, basically, you're trying to rank your inputs, how important each of these is. Try it. Get one of your quants to do it. Yeah? I did it, right? I did it with weather, so that everybody understands. I did it for you all. So I got one of my engineers to say, predict whether it will rain or not rain tomorrow at San Francisco Airport, where we are, right? And I say, by the way, engineer, you're not allowed to use any physics. Forget about all of it. Forget about all the thermodynamics equation. Forget about what the meteorologists say. Meteorologists spend 20 years in school figuring out thermodynamics equation to predict the weather tomorrow, but you are only going to use 4 decades of daily records for San Francisco Airport and then guess whether you rain tomorrow. He put it through a machine learning algorithm. We'll go into those details later, but just understand how it works. Take all the 10,000 past records. Now, we didn't get 50,000, 10,000 daily records, each record, right? And then rank what matters. It turns out those were what matters at San Francisco Airport. Take some time to digest this and correlate with your own work, right? What matters to the ultimate prediction? It turns out that he took 20 different things, and 10 of them came out to be more important, and the remaining 10 were close to 0 matters. Turns out that if it rains today, there's a 14% contribution to the fact that you'll rain tomorrow. Think about that for your own work. Right? What matters to this prediction? Collect all those records and send it through a machine learning algorithm. We'll talk about those later. And we just did a simple exercise. So a meteorologist predicts San Francisco Airport rain or no rain at 95% accuracy. So I asked my engineer, how did this do? 60%? 70%? 82%. Now, it is not 95, but just first try, without tuning the algorithm, he got 82%. It's pretty much like, these two models, top-down. This is pretty much like someone going to school, spend 20 years, get a PhD in the science, and then when you ask the engineer or scientist whether this bridge with this I-beam will hold, this scientist or engineer will sit down, work out all the equations, run through simulation, and say, yes, it will hold. In this example, you have someone not going to school, but spend 30 years in the construction industry, observing bridges, and then you ask this senior person whether this bridge will hold. He'll say, yes, right? And you ask him why, he say, I don't know. I just know it. Here, he or she will know. He will show you the equations, you see? So these are the two approaches. It takes some time to get an answer here, but after gaining your experience, it is very quick. Pros and cons, yeah? Right? So now that I've given you the grounding of top-down, bottoms-up, let's look at some of the world's example where Google, Facebook, Apple have been investing massive amounts of monies in. Because this is going to decide the type of tools your quants or your analysts will get, because it's coming from them. So what do they measure in terms of artificial intelligence? The bottoms-up, top-down approach here. They use games. I used the word brain. I meant human brain, yeah? Yeah, okay. Right. In '97, we know that Deep Blue beat the world top chess player, Kasparov. This particular board position was when Kasparov conceded. So keep that in mind, right? The last bastion of human power for chess, right? The number of combinations is 10 to the power 47. If you want to work through a table of all the different chess positions, it's 1047. You know how big this number is? It is a crazy big number, right? Right? If I took all the computers on Earth, everybody's, Google, Amazon, yours, put it together, ran it for 100 years, I'll only get 10 to the power 30. This is a crazy big number. This tells us that we don't solve chess. We only need to be good enough to beat humans. Eh? So keep that in mind, right? AI systems currently, all the huge investments are goal towards beating humans, not solving problems fully. Right? For that, you need top-down. Okay? Is there a simpler game? Yeah, few people know 2 years before that, the machine beat the world top checker player. 10 power 20 is closer. It took 18 years for University of Alberta to finally solve checkers. Of course, they did it the smart way and didn't have to go through all the 10 power 20 combinations. Yes? Guess what the paper published by University of Alberta says as a conclusion after 18 years of computation? If both players don't make a mistake, it will always be a draw. So imagine, right, after 18 years, at the end of the conclusion, it will always be a draw, right? Yeah. Well, I can believe that because of the symmetry of checkers. And is there a simpler one than checkers, by the way? Yes, tic-tac-toe. We all know this. It'll always be a draw, right? So these are some things I want you all to note, right? There's a reason for these examples as you correlate with your applications, yeah? So is there something tougher than chess? Yeah, brilliant. Kevin, Craig, 2 T-shirts. Right, there we go, Go. Now, Go is a crazy, crazy, crazy big number, right? 10,171. Rules and searchers wouldn't do it. Yeah, so they needed something different, right? So they used a new method of bottoms-up called deep learning that more recently come up. Later, I give you a taxonomy to see where they all sit, but don't worry about what that means at the moment. They use deep learning, and finally, one of the top Lee Sedol, Go player, was beaten. There is something to note, 2 things to note here. One, when the developer of AlphaGo was interviewed, Hassabis, he's actually a UK guy, so many of you are from the UK, right? Yeah. Right, was interviewed, why did your AI software make this, what they call a godly move, yeah? Magical move that beat Lee Sedol? You know what he said? I don't know. Yes. So deep learning is opaque. We'll come to that later. So another thing to note, just like here, right, when you have an experienced person looking at a bridge and say it will hold, likely he cannot tell you why. He just knows it. You get the same problem here. So AI software can give you a new perspective, but sometimes they cannot tell you why. Keep that in mind, yeah? The regulatory people will have an issue with that, right? Yeah, you're not alone. The drug design companies have the same issue, right? The machine tells them, this is a great drug, But then say, oh, okay, it's machine telling me, how I'm going to tell it to the FDA, right? So of course, they go back to the top down to validate what the machine is saying bottoms up. And then they present the top down approach to the FDA. Yeah? Things to learn here. So is there something tougher? Oh, the second thing about this is, if you can find this picture, this particular picture, that was the last move, yeah? By Lee Sedol. Keep that in posterity because this is the last bastion of human beating over machine. He won this only one game. Yeah. After that, he lost. Yeah. So last bastion of human ingenuity, right, is here. No, I'm just joking. Now, is there a game tougher than Go? This one, you get more than a T-shirt, right? Yeah. Poker, right? Now, the combination is less, but there is one thing about poker that makes it tough. Yes, it's incomplete, right? All the other games, you know what your opponent pieces are. In Texas, heads up, no limit poker, hold'em, no limit poker. The cards are hidden from you. This makes the AI software even more complex. So now you have incomplete information to feed past records in for deep learning. So what are you going to do? You give it a law to patch up the fact that your information that you're feeding the machine is incomplete. You see the word law there, right? And what law did this software use that I was involved with CMU? Nash Equilibrium, it turns out. So don't just think of Black-Scholes, right? Nash Equilibrium will become more and more important, even so after the movies, right? Because it is good at figuring out behaviors in a negotiation, especially if you don't know what the other parties have. So in 2016, before 2017, we went out and played against the world top 4 poker players. We lost $700,000, virtual money. Yeah, yeah. So Professor Sandholm, right, and us worked together to build a machine 10 times faster. In January 2017, we came back. We beat the 4 world top poker players, $1.7 million. So we made back the $700K and went ahead by $1 million, right? Virtual money, right? The next message here is scalability. Machine learning algorithm can scale. It's just how much you're willing to invest in gobbling up all the past records. Of course, you need to be smart about it, right? To train your system. To recognize human faces in an unsupervised learning environment, Google took 30 million images here, right? Better if it's supervised. Yeah. Oh, by the way, it's like the Wild West now, right? There are poker players coming up to the machine and say, I want to compete against you. So far, it has not lost since January. It's even been paid to go to China against the top poker players. It won. To the extent that Professor Sandholm became a celebrity at the airport, right? At Beijing airport. Yeah, right. So remember, these numbers are big. Therefore, typically AI software don't solve problems. They just give you a good prediction and can't tell you why, many a times. But they can scale, right? Now, it takes a kid years to get a college degree. But wouldn't it be great if a grade 1, first grade student goes in the morning and comes back with a college degree in the afternoon, right? Now, that's what the machine can do if you're willing to invest in it, right? And finally, it's asymmetric, meaning it is front-heavy, meaning it takes lots of compute power to learn, to train, but then by the time you've trained up all the weights and relative importance and input ranking, those are very lightweight that you can put on remote devices, and they can make predictions very quickly. It's back-heavy, front-light. And that's part of the reason why, for the mission to Mars, yes, we have put one of these inference engine, the front light engine, on the space station. The arrow is where it is. Yeah, because as you travel further and further from Earth, you need to be able to do predictions on your own faster. So machine learning algorithm that has been pre-learned on Earth with all the heavy duty done, and then you carry all the lightweight input rankings to do predictions. Yeah. So I have a minute left. I'm just going to give you a quick taxonomy, right? Artificial intelligence, 2 ways to do it, remember. Your traditional way is top-down. Your quants, your analysts, your data scientists are starting to look at the bottoms-up approach. Embrace them. They do not replace, the bottom-up doesn't replace the top-down, but it gives you a new perspective. And I've seen scientists that realize that their top-down approach for years have been missing something. And it was pointed out too by the bottoms-up approach. I got goosebumps, right, when the scientist came to me with that realization, with that anecdote. At bottoms up, sometimes you predict a point. That is, where will that stock price be tomorrow, right? Sometimes you predict a category. Should you buy or sell? Yeah. And then they use regression there. Don't worry too much about it. If you hear it, that's basically what it is. It's basically you get a splatter of points, find me a nice line that is the best fit for all those splatter of points. Yeah? So that line can be extended to predict the future. Regression. Category, you got classification. If your data is labeled, this is a picture of a cat, this is a picture of a cat, this is a picture of a dog, this is a picture of a human, and you send it all to the system, and at least the system has something to go by. Right? Reinforcement learning is when you take two machines, learned machine, and get them to compete against each other, and the teacher step back. And that's what happened with the Go software. It stepped back so far because the two machines have been learning from each other, right? To the extent that ultimately it became so opaque that the developer doesn't even know why the machine is making those decisions because of reinforcement learning. Right? Just like kids, right? After you teach them in first grade, the kids go out and play for 3 years and they come back. The teacher don't quite know how they developed after that, right? Right? Yeah, there we go. Now, if it is unlabeled, this is new frontier. You give me lots of stuff and I have not labeled them. Yeah? And then don't worry about the back end of it. All these different random forests, deep learning, Bayesian, K-means. Don't worry, because all these are the relationships to all this that leave it to your quants. Okay? You just know the high-level concepts and you test them. Okay? I close this session with this video. Sorry for going over. And just watch this. Yeah? Oops. Oh, yeah, never mind. I keep going. There's work to do. Okay, let's work. Ooh, not so nice. Even not. Raise your hand if you felt a little bit bad for the robot. Yeah, this is 2015. Imagine what you would be like 10 years from now. On this note, thank you, Craig.
Appreciate you very much for joining us this morning.
Thank you. Thank you. That's Brad over there. Raise your hand. If you have further questions, go to him at the HPE booth. Yeah? Thank you. A plug here. Thank you again. Yeah. Yeah.